Alrighty, let's talk about the pink sheets. Reasons to be used in geometry proofs, theorems, postulates, and definitions. We will reference this page when using segments and angles. Okay, so the segment addition postulate, which states that if B is between A and C, then AB plus BC is equal to AC. So let me go ahead and draw an example. So I have a segment right here, and it has endpoints A and C respectively. Now, if B is between those two endpoints, it should look like this, right? So what the segment addition postulate is saying is that if you have a part plus another part, well, if you glue them together, you're going to get that whole thing. Hence, the AB plus BC is equal to that whole thing here, AC. So, part plus part is equal to whole. Here, we're going to go ahead and talk about the definition of midpoint, and this does involve segments. So if M is the midpoint to segment AB, then segment AM is congruent to segment MB. And notice that you have these arrows going both ways because it's not going in one direction. It's not if and then, strictly. It actually goes both ways. You can say if segment AM is congruent to segment MB, then M is the midpoint of segment AB. So this is a biconditional. So it goes both ways. Okay? So here, let me go ahead and draw this picture. Again, we're dealing with segments. So here is my segment here with these endpoints, and then M is the midpoint between those 2 points. What is the result of having a midpoint there? Well, that means that this segment is congruent to this segment, and we draw tick marks to indicate congruency. So that means that 1 tick mark for segment AM and 1 tick mark here for segment MB. So this is saying part is equal to part. Okay, now the angle addition postulate, which states that if point B lies in the interior of angle ADC, then the measure angle ADB plus the measure angle DBC is equal to the measure angle ADC. That's a lot. Let's draw a picture to remember what is going on, because we've talked about the angle addition postulate, but let's go ahead and draw a picture so I can jog your memory. So if we're talking about angle ADC, it should look something like this. So here's A, and then D is the vertex, and then here's C. And if you have point B, which lies in the inside of angle ADC, it should look like this. Here's point B. So that means that this is my whole angle, right? Angle ADC. So if you have a part of that angle plus another part of that angle, then you're going to get the whole thing there. So it's like the segment addition postulate, which is really part plus part is equal to a whole. Okay? Now, let's take a look at this. If angle AOC is a straight angle and B is any point not on line AC, then the measure angle AOB plus the measure angle BOC is equal to 180 degrees. So that key word, straight angle, let me draw angle AOC. Should look like this. So here's A, here's O, here's C, and then B is any point not on line AC, should be right here. So then I'm going to connect that and see that this is a straight line. This is a straight angle, so they should be 180 degrees. So you have this part here, which is sorry, I need to label this B. So you have this angle here, this part, which is measure angle AOB, and then I have this other part, measure angle BOC. That's gonna add up. That's gonna add up to 180 degrees. So when this is an example of a linear pair. These angles that are stuck together and then form a straight line, which will add up to 180 degrees. So linear pair is basically a straight angle. Okay. The next one, definition of angle bisector. So this is a biconditional, it goes both ways. If ray OC bisects angle AOB, then angle AOC is congruent to angle COB. Or if angle AOC is congruent to angle COB, then ray OC bisects angle AOB. Again, that's the definition of angle bisector. So let me go ahead and draw this whole angle AOB. So here's A, here's O, here's B, and then here is ray OC. So what's the result of having that ray being that bisector of angle AOB? Well, that means that this angle here is congruent to this angle here, and we use these arcs to indicate congruency. So one arc there, hence the angle AOC being congruent to angle COB. Okay, now we need to know something. It's called definition of congruence. Because we've talked about this at the beginning of the semester, I want you to understand what the difference between the language of geometry is versus the language of algebra. So this, for instance, we have segment DE is congruent to segment FG. Whenever you're using that symbol congruence, you're talking about shape compared to another shape. And this is the language of geometry that we're using, as well as the segment bars here for segment DE congruent to segment FG. And here we have another shape, and we're using that congruent symbol here. Again, this is all in the language of geometry, this congruent to this, okay? So this is just me naming shapes, or overall you're just talking about or referring to shapes in general. And then over here, this is in the language of algebra. When you're talking about numbers, or when you're talking about values, when you're dealing with solving equations, you are referring to the language of algebra. Okay, so this is saying the measure of DE is equal to the measure of FG, or DE is equal to FG. Measure angle R is equal to the measure angle S. See, we don't use the segment bars, we get rid of them and refer to them as, numbers and such. For angles, we use the letter M to talk about the value of that angle, like how long is that angle, right? And again, we use these equal signs to talk about algebra. We're solving 2 + 2 = 4. That's the language of algebra, okay? So hopefully that makes sense. But when we get into proofs, you will see why we're going to be using the definition of congruence as a reason. Here, reasons to be used in geometry proofs, theorems, postulates, and definitions. Reference this page when using special pairs of angles. Okay, the vertical angles theorem. If two angles are vertical, then they are congruent. So let's draw a picture. You have these two lines, and they intersect. Note the width of this angle to this angle. That means that they are congruent. So here, these are congruent, and then this angle here and this angle here are also congruent. So that and that are congruent. And we can call this angle 1, angle 2, angle 3, and angle 4. So let's take a look at what we need to write here. we're going to write angle 1 is congruent to angle 2 because vertical angles theorem, they are congruent. We just look across. And then angle 3 is congruent to angle 4, again, vertical angles theorem, and we look across, okay? So this is something that we've already talked about at the beginning of the school year. Then let's talk about definition of complementary angles. If two angles sum up to 90 degrees, then they are complementary angles, and it goes either way. If they are complementary angles, then the two angles sum up to 90 degrees. So here are some two examples of complementary angles. Two angles that are separate, but they add up to 90 degrees. So here we call this angle angle A, angle B. This is 20 degrees, and this is 7 degrees, 70 degrees. So these angles, they add up to 90 degrees. Or you can have something like this where they are stuck together. So you have something like this. You can say that this angle is 30 and this is 60. So this part plus this part is going to equal to this 90 degrees here. And call this angle X, Y, Z. There we go, angle X, Y, and Z. And then we can call this W. All right, so here we go. We know that here, this is measure angle A plus the measure angle B is equal to 90 degrees. And I'm talking about, this is the language of algebra. And then here, we can say that measure angle XYW plus measure angle WYZ is also 90 degrees. Okay? I will never say measure angle A plus measure angle B is congruent to 90. That doesn't work like that. Or I will never say angle A plus angle B is congruent to 90. That's not what you're supposed to do, okay? All right, here we go. Definition of supplementary angles. If two angles sum up to 180 degrees, then they are supplementary angles. Again, this is a biconditional, so it goes either way. You can say if they are supplementary angles, then the two angles sum up to 180 degrees. So I can draw something like this. They're separate. Right? We'll call this angle A and angle B. So we can say that the measure, oh, sorry, this is not right. That should be 150 degrees. Okay, so we can say measure angle A plus measure angle B is equal to, well, 30 plus 150, that's 180 degrees, okay? Or if you have something like a linear pair, y'all, if you have something like this, let's see, let's call that A, B, C, D, and this is 130, and this is, I don't know, 50 right there. Then you can say that because by the thing about linear pairs are supplementary. So measure angle ABD plus measure angle DBC is equal to 180 degrees right there. And this is, again, a linear pair. Oh, look at that. Linear pair theorem. If two angles form a linear pair, then they are supplementary angles. And it only goes one way. You cannot say that supplementary angles are linear pair, because I can provide a counter example, which, you know, is this. This is an example of supplementary angles, but they aren't linear pair. Right? They don't form a linear pair. So it only goes one way. So if two angles form a linear pair, then they are supplementary angles, which I've already drawn right here. This page is essentially algebra. Reasons to be used in geometry proofs, theorems, postulates, and definitions. Reference this page when using algebra. Okay? So we say the addition property of equality. If A is equal to B, then A plus C is equal to B plus C. This is essentially saying is that, okay, you have like 2 is equal to 2, And then if I add something like, if I add 3 here, then I add 3 here, you need to balance the equation so that 5 is equal to 5. Over here, when you see that A plus C is equal to B plus C, if I'm like giving you an example of an algebra problem, like 2x minus 3 is equal to 5, right? And my goal here is, if I want to get 2x by itself, well, you're going to have to add 3 to get rid of that. And then whatever you do on one side, you have to do on the other side. Okay, and that is really what the addition property of equality is saying, is that whatever you do on one side, you have to do on the other side, and that only involves when you are adding. So this is the addition property of equality, okay? That adding 3 on both sides is the addition property of equality. That's the step, that's the reason. So let's say you have something like the subtraction property of equality. Again, whatever you do on one side, you have to do on the other side. If I do, let's say 4 is equal to 4, right? A has to equal B. A is 4, B is also 4, and I'm subtracting 3 here, but I get like 1 equals 4. To balance that, I have to do the other side too. So that's going to give you 1 equals 1. And if I were to give you an example, okay, so if A is equal to B, then A minus C is equal to B minus C. Let's give you something like 4x plus 1 is equal to 9. Okay, my goal here is to get that 4x by itself, but that 1 is in the way, so I need to subtract both sides by 1 just so I can have that term by itself. And that minusing 1 on both sides is essentially the subtraction property of equality. That's the reason there. The multiplication property of equality states that if A is equal to B, then AC is equal to BC. And my example would be like, okay, I got 1/2 x right here equals 4. Okay, to get x by itself, or get this by itself, I need to get rid of the number that's in the denominator. And to do that, well, what's the opposite of division? Well, it's multiplication. So I need to multiply this whole term by 2, and whatever I do on one side, I have to do on the other side. So that's going to go away, and then this is going to give me x is equal to 8. Okay, so this multiplying by 2 here is the reason, the multiplication property of equality. Multiplication property of equality. The division property of equality states that if A is equal to B and C is not 0, because you don't want to have, because if you divide by 0, then undefined. You don't want that to happen. Then A over C is equal to B over C. So if I give you something like 4x is equal to 16, and I want to get x by itself, well, I'm going to divide both sides by 4, and that is the division property of equality right there. Okay, and the distributive property is something that we know and love. If you have a number in front of the parentheses, you are going to distribute and you get something like this. Or if you want to essentially factor, that's still using the distributive property. Notice that I have an A here and an A here. That means I can factor the A, so I will get B plus C. Okay, so this goes both ways. Okay, next, references page when, again, using algebra. The reflexive property states that it's basically a mirror, like a reflection, right? Mirror. The reflexive property is A is equal to A. It's like saying 5 is equal to 5. Segment DE is congruent to segment DE, and angle A is congruent to angle A. It's basically the same thing. And then the symmetric property states that if A is equal to B, then I'm just swapping the position. Then B is equal to A. If segment DE is congruent to segment FG, then again, I'm just swapping the position. FG is congruent to DE. If angle A is congruent to angle B, then angle B is congruent to angle A. I'm just, again, swapping the position. Substitution. If A is equal to B and x plus a is equal to y, pay attention. If a is equal to b, and here's a, then what's the result of that? X plus, well, where's the a? It got substituted, so it's now x plus b is equal to y. Okay? You're basically replacing with something equal. Okay? Lastly, the transitive property states that if a is equal to b and b is equal to c, then a is equal to c. So look at this. If a is equal to b, and we know that b is equal to c, well, can we say that a is also equal to c? I'm just literally thinking about the middle term linking the first and last together, right? So here's my first, here's my middle, and here's my last. If a is equal to b and b is equal to c, well then I don't need this anymore. A is equal to c. And that's the same thing over here. Segment DE is congruent to segment FG, and segment FG is congruent to JK. Then logically, since we know that these things are equal, right, this is also segment DE, which is congruent to segment JK. And then that's the same thing. Let me go ahead and give you an example, like an algebraic. If 2 plus 3 is equal to 5, and 5 is equal to 1 plus 4, well, I don't need this anymore, because 2 plus 3 is equal to 1 plus 4, which is true. This is 5 and that is 5, right? So really, let's write a summary. Think about middle term linking the first and last together. Think about middle term linking first and last together.